who needs, at least in the algorithms community, no introduction. Andrew Goldberg has done very important work in algorithms and algorithm implementation for many years, starting with max flow and min cost flow, then in work with his colleagues at Microsoft, research on routing in road networks, and on and on. He's helped guide us in what makes an algorithm implementable and practical. So I'm pleased to see he's going to be speaking to exactly that topic today.
Okay, so I'm going to talk about challenges in research on practical algorithms, and both industrial challenges and academic challenges, and I conclude with some ideas for collaboration between industry and academia. So, so the views I present are my views, and they're mostly in the context of practical algorithms, but many of the points I make apply to other research areas. And for algorithms, it's if you're in industry, have an algorithm that works. Is it all you need? And the answer is no, because you also want to know why it works. Because if something changes, like your business scales or you introduce a new feature, you may suddenly be in a situation where the algorithm no longer works if you don't understand why it works. And you want to be ready for that. So basic industrial research in general, and in algorithms in particular, is disappearing, which I think is bad for science in general. And so algorithms research now in industry has to be done in production environment, which is an interesting change. And I want to sort of mention an old joke. So the relationship between theory and practice is theory when you know everything but nothing works in practice, and practice is when everything works but you don't know why. And when you combine theory and practice, you get that nothing works and you don't know why. So we want to combine theory and practice in a different way. Okay, so academic research problems. One is oversimplified models. And many real-life requirements are proprietary or complex, and academic research focuses on simple, clean models. And then it's a question of how well the simple models relate to real life. And you still can learn a lot from simple models, but there is a huge gap between sort of clean problem solutions and real life solutions. So an example is in navigation systems, turn costs. So we all know that if you make a turn, you have to slow down, and if it's a right turn, it's usually faster than the left turn, and if the intersection is busy, it takes longer than if the road is empty, and so on. So this is something which was ignored by algorithms researchers, because basically the belief is, oh yeah, we will introduce this turn costs and all algorithms will be affected in a similar way. And we were somewhat surprised that on real data we observed that in fact, if you introduce these turn costs, the algorithms are affected in a different way. And at that time, we were working at Microsoft, so we had real data, but we couldn't share this data. But the nice thing was that we did a little bit of experimentation, and we showed that adding 100-second U-turn penalties to public data allowed us to reproduce this phenomena. Okay, so we actually could share it with academic community so that they can study it. And you can see that, in fact, the difference is big. So this was our new algorithm, which we're introducing, customizable route planning, and the competition was contraction hierarchies. And the relevant metric here is time metric, because as far as distance goes, turns don't add to distance. But for time, there's time cost. And here is no turns, so all turn costs are 0. And these are different representations of turn costs. And you can see our algorithm, which was designed from ground up to handle turn costs, it wasn't really much affected at all by introducing of turn costs. And contraction hierarchies algorithm was affected, and preprocessing time increased by more than an order of magnitude, and so did preprocessing space. And for queries, if you use the big graph representation, the time went up by less than a factor of two, but for a compact representation, it went up by almost an order of magnitude. So it's a huge difference for this algorithm. And it's a relatively simple thing, right? You would assume it doesn't make a difference, but it may. Okay, and so I was working for a while on vehicle routing, and these are government EU regulations for truck drivers. And if you are designing a practical vehicle routing algorithm, you have to take this into account, because otherwise your drivers will be fined all the time. And and they make sense from safety reasons. So like daily driving period shall not exceed 9 hours, with an exception of twice a week when it can be extended to 10 hours. And there are more regulations like that. And if you think this is all, there's another page. And if you think this is all, by the way, there's a web page where you can read all of this. I just want to make a point that it's complex. And if you think it's complex and not complex enough, there are also cabotage regulations, which are also as complete. And we all tend to think that the EU is a happy free trade family, but in fact, at least as far as truck drivers go, countries want to protect their own drivers. So they put restrictions on how much a foreign driver can work in a different country, which leads to this kind of regulations, maybe even longer. And so this has algorithmic implications. So, of course, academic studies ignore most of these constraints. And it's already, vehicle routing is already a very, very hard problem. So even without all of these constraints, there's a lot to do. And certainly academic research generated lots of interesting ideas. But it's very hard to say without actually re-implementing everything of how this will work in practice and what works better. So let's consider a common algorithmic approach, which is column generation using constraint shortest path to build routes. And if you don't know what it is, don't worry. I just want to make a high-level point. So constraint shortest path algorithm sort of grows a partial path, and it has a state associated with it, which basically captures the usage of resources by this path. So for a driver, it would be how much driving time you consumed, when your last rest period was, which countries you visited, when, and so on. And the point is that the algorithm, the problem complexity depends, at least complexity of algorithms which use this approach, depends on the size of the state. And in theory, I suspect the dependence is exponential. What it is in practice, it really depends, but it really strongly depends on the state size, and the more constraints you add, the bigger the exponent becomes. So it's something that really affects performance. Okay, so another thing is public benchmark quality, and benchmark qualities are really vary. And it really depends on how careful people in the area who are creating benchmarks. So something like linear algebra or traveling salesman has really, really good benchmarks. In some other areas, benchmarks are iffy, but they evolve. So one example is maximum weighted independent set benchmarks. So the original one, which is still heavily used, comes from the second Dymex challenge, which was on hard problems. But maximum independent set was not the main focus. So they basically, what they did was they had some click problems. So they took complements of click graphs to get maximum independent set problems. And then they did node ID modular constant weights. And of course, these are not realistic weights. And even if the original graphs came from real applications, which they had many synthetic instances, if you take a complement of this graph, it is an iffy graph. And in particular, most real-world graphs are sparse. These graphs are dense, and they have funny structure and so on. So this is not really a good benchmark, but still heavily used. There are other benchmarks, for example, those from map labeling applications. They're better, they come from real application. But what we discovered was that we had a vehicle routing problem with, which generated some maximum weight independent set subproblems. And vehicle routing is great because it's a multi-billion-dollar industry. So if you save a 0.25%, it really matters. So you really want to solve big problems you get from this application as close to optimal as you can. And what we discovered is that these problems have different structure, different size, and different relative algorithm performance. And we actually published a paper on solving this kind of problems. And also we published the data set, which was not easy, but we have it. So in case you're interested in big real life maximum weight independent set problems, you can download them. Okay, so the point is that it's still very hard to get real data if you are in academia. Okay, so industrial research, basic industrial research is in a bad shape, and it's sort of a shame, I think, for science and computer science in general. Some highlights of industrial research is Xerox Alto was essentially a PC with a graphics user interface, which was a decade at least ahead of its time. And another example is Alta Vista, which was arguably the first really successful search engine, which sort of disappeared. And there are high-level problems. I mean, you can put fault on everybody of why industrial research, basic research is disappearing. I mean, it's certainly inability to monetize, high-level management, and ability to see the value of research, researchers and research managers not always doing something which company would be interested in, or not being able to explain why it's good, and so on. But it's a fact that, unfortunately, there are very few places where, industrial places where people can do full-time basic research. And in algorithms, most researchers have very limited time to do basic research. And it's unfortunate because research is actually a full-time job. Okay, but something which is very specific to algorithms is commodity software engineers. So, you know, when I was a PhD student, most programmers had advanced degrees in math and physics and computer science, so they could really learn complicated things. And also, as far as data structures go, there were many fewer things to learn than there's now, right? Because computer science develops very fast. There are new algorithms, data structures, you know, new learning models, new systems, things which are being discovered. So there's much more to learn. And you get sort of a random undergraduate from a random university, which probably would be somewhere in India. And you cannot expect them quickly learn really sophisticated algorithm. And also, but you sort of need software engineers to take over and maintain production code and work with it. And also education now, since there's limited time, is for software engineers, it's based on specific programming languages and software development environment. And this is okay because vast majority of code is like UI or data interface or something where it's relatively easy, right, for user interface. Okay, there's a red button here and a blue button here, and if you click on it, this is what happens, and so on. You don't really need a PhD in computer science to understand this. And also, you substitute language features for detailed knowledge. For example, in Java, you can use parallel stream and not know anything about locks or concurrency or race conditions. And for most cases, this is fine. But if you want to implement a sophisticated, really highly tuned parallel algorithm, you probably may want to go deeper. But then you have to have a lot of knowledge about concurrent systems. Okay. And there is an example which was, I think, a SODA invited talk by Arjun Lenstra, which sort of shows that a little knowledge is a dangerous thing. And we all know that an RSA key is a product of two large primes. And so what you do is, and also we know that primality testing is efficient. So what you do is you start with a random number, and you keep incrementing it by 1 until you get a prime number. This is your first prime number. And then you do it again. You take a random number, keep implementing it until you hit a prime number, then you multiply these two numbers, and you get a number which is hard to factor. And of course, this is, at least Langstra claimed that this is a real-life example. So some programmer decided that why would you call a random number generator again? You just take this first number, and you keep adding 1 to it until you hit another prime number. And can anybody see what's wrong with this?
It's the cycles of timing attack.
Sorry?
A timing attack. You can tell the difference between F2 and F1 by seeing how long it runs.
No. No, I mean, you use this to generate the key, so it will run in a different environment. Yes?
Just take the square root.
Exactly. Taking square root is easy, so you can factor a number again this way really, really easy. But if all you know is that you need to take two big prime numbers and multiply them, you wouldn't know that this is a bad thing. So a little knowledge is dangerous. You really, to work with sophisticated algorithms, you often really need to understand what goes on sort of much deeper than at a very high level. Okay, and actually I have a whole talk on what happens when software engineers take an efficient prototype code and productize it. It's a whole different story. Okay, and also project managers. There are lots of managers with no science education, and it's sort of one-size-fits-all methodology because most projects implement a data pipeline or user interface or something. And so, today you are doing a red button, and tomorrow someone else will do a blue button. And so software engineers are treated as fungible. But when you go to algorithms, there's a steep learning curve. Even to understand an algorithm on high level, it takes time. And to understand deeper, it takes time and also certain background. And so because of that, there are issues introduced during technology transfer, feature addition, and maintenance. And also often it's not like you implemented something, transferred it to production and forgot about it. Because often what happens is you're in a business which is evolving and growing. So problem size is growing, features are added, and so on, and you need incremental changes to production code. And unfortunately, scientists have to really supervise this process at low level to avoid problems. And you sort of need to do work with production code, do code reviews, and so on, which is in a sense winner's curse. You have some great system transferred to production, but then you're stuck forever with basically helping to maintain it and make sure that it doesn't get screwed up. Because otherwise, it's very likely will get screwed up. Okay, and let me finish with some fairly obvious points on industry-academia collaboration. So what is something which unfortunately not every company understands is there's big value in industry in collaborating with academia. And the most important one, you can leverage academic research potential. There are lots of people in academia who want to solve real problems, who have time to do basic research, and they would be happy if they know what real problems are. And also, this way you'll get graduating students who are better prepared for industry. And the way to contribute is industry can contribute real life data and publish results and do presentations about results. And also can hire interns or have faculty spend sabbaticals there. But these two are actually in some companies are very hard, because basically management doesn't see this value proposition, so nobody wants to take risk. I mean, if we release this data, I don't see what good will come out of it, but maybe I'll get fired because there's some privacy leak or something. So this seems like an obvious no-brainer, and some companies are really good about this, but many companies are not. So in terms of academia, the benefits are more relevant research potential, and also potential for research to do real-life implications. And what I mean by that, many of you are probably familiar with work on John Kleinberg, which he did on Facebook data. And he really got some interesting results about Facebook users, which I think got right up in New York Times or some other major news outlet. So, and also you get students which are better prepared for industrial career, and not all students stay in academia, as you probably know. And the way to contribute is, I think algorithm scientists should have strong software engineering skills. They should be able to work with real code if they go to industry. Also, it's in many areas, it's good data sets are missing, and also the good data sets are not evaluated and sufficiently recognized, I think, by the community, which sort of, if you're in industry and try to release a data set and you're in a company where it's hard, you may decide that it's not worth it. So somehow recognizing it better, I think it's good. And also, I think doing startups or spending sabbaticals in industry is a good way to learn about real life. So this is all I wanted to say.
We have time for one question. There is one.
Yes. Do funders ever require release of real data sets?
Sorry?
In the bio world, the NIH requires release of data in a lot of, circumstances, or at least, budgets money for public databases. Does that happen in the algorithms world?
Not really, and also sometimes it's hard, because when I was at Microsoft and we worked with Facebook data, actually there's an agreement that if Facebook asks for it in 24 hours, we remove all traces of this data, which makes it very, very hard. So, I mean, it would be nice, but many companies just will not do it. And also, if you know about privacy, it may be legitimate, because there's some user data, there may be some proprietary information in the data. So I don't think it's feasible. But when it's feasible, it's very, very desirable.
Do you have anything to say? I remember the Netflix challenge where you were supposed to fill in, the missing movie ratings. And, that sparked a really, really great algorithms research. So
They got into trouble.
they did.
They got into
But-
big trouble.
Oh,
Yeah,
Netflix did.
Yeah.
So it's not a good
I don't
example.
know the rest of the story then.
No, but I have to say that in our research on routing algorithms, like navigation algorithms. There was a German company which released data which was very, very helpful. And also, so there were some other public data sets, real data sets, which I think was one of the reasons why this research was so successful and why now your phone can compute your route in a fraction of a second.
All right, I think we have to, I just have a comment. ML Commons has public data sets that people can download.
Yeah, it really varies from area to area, but it's in general it's a challenge because of proprietary and user information concerns. And these are valid concerns, but still it shouldn't prevent data to be made public as possible.
Okay, let's thank Andrew Goldberg once more.